Now let's have a closer look at some specific technologies of UMTS, technologies that differ from GSM. As already mentioned, UMTS is a CDMA technology. How is CDMA applied? Well, you remember CDMA, chipping, spreading of codes, using the right chips, orthogonal codes. If you cannot remember, please do have a look at those sections of the lecture. So, how is spreading and scrambling of user data done in UMTS? First of all, UMTS uses a constant chipping rate. A constant chipping rate of 3.84 megachips per second. You might ask why 3.84? That is not 2 to the power of some natural number. So yes, it was 4096 kilochip per second. And then due to these discussions, patent fights, whatever, the agreement was made, okay, we use the 3.84 megachip per second to avoid further problems. So, additionally, UMTS uses a constant chipping rate. A constant chipping rate has certain consequences. Think of different data rates you want to support. Think of whatever I want to support 1 megabit per second, or I want to support 10 kilobit per second. If you use a constant chipping rate, that means you have to vary the spreading factors. Using the same spreading factor, let's say a factor of 10, same factor for different data rates results in different chipping rates with a factor of 10, for example. Now, UMTS has a fixed constant chipping rate, 3.84 megachips per second. That means to support different data rates, you use a fewer number of chips per bit for higher data rates and more chips per bit for lower data rate. So this is the way how you can adapt your different data rates to a constant chipping rate. But what are the consequences? If you have more chips per bit, that means you spread more, higher spreading factor, that means more robustness. Less spreading, lower robustness. So think of different applications for that. So maybe a not that important but high data rate stream, yeah, that's fine. Lower spreading factor and lower data rate, but maybe very important control data, that fits as well. Okay, that much about the spreading. So now, how do we apply the code multiplexing? There are different ways. First of all, the users are not separated via orthogonal spreading codes. So spreading here is not used to separate the users, but spreading is used to separate different data streams inside a sender. You have a data stream 1, you apply a certain spreading code. Data stream 2, yet another spreading code, and those spreading codes have to be orthogonal. So inside a sender, all the spreading codes are orthogonal. You know what orthogonal means. So that's quite a simple scheme, because you do not have to manage orthogonal spreading codes across different systems, but only inside a single system. So that's much simpler management of the code. So each station can use the same orthogonal spreading codes. So you see, for example, code 1 is used in sender 1 and also in sender 2. How to separate different stations? Well, this is what UMTS uses the scrambling codes for. The scrambling codes, they are more or less orthogonal. And these codes, they are used for performing the code multiplexing, the separation of the different senders. So senders and receivers know the scrambling codes, and scrambling codes do not further spread the bit stream. So the spreading code, they perform the spreading of the data stream with the help of the chips. Then, exactly at this stage, we already have the 3.84 megachips per second, and then we apply a scrambling code that is only there to separate the different senders, but not to further spread the stream of chips. And then we send the data over the air, signal superimpose, and then the receiver, knowing the scrambling codes, can then actually de-scramble the data depending on the senders. And then you perform the de-spreading, knowing the spreading codes, and then you have the original data again. Big advantage is that we do not really precisely have to synchronize the different senders. The scrambling codes, they stay more or less orthogonal, no matter how you apply them. So these are special codes without going into further details. So this is exactly where you apply the CDMA inside, or the CDM, the multiplexing inside the station to, well, perform the multiplexing between different data streams. And then again a code multiplexing to separate the different senders. That's the idea. Now, how to get the spreading codes? UMTS uses a very simple scheme for that. UMTS uses the so-called orthogonal variable spreading factor coding. What does that mean? You construct a code tree in the following way. If you want to double your spreading, and you see from this scheme you cannot have arbitrary spreading, so you want to double your spreading, you construct the child nodes in a very simple way by concatenation. So concatenation XX or X and then all bits flipped. That's the way how you actually construct the child node from the parent node in this tree. So on the right hand side you see the example. This is implemented in all the devices. You start with a spreading factor of 1, so no spreading at all. And then you construct the subtrees by concatenation 1, 1, 1, minus 1. Remember, 1 could be a logical 1, minus 1 could be a logical 0. And then we construct the spreading factor of 4. So there it starts to be useful. Before that, it's not really big spreading. But okay, so we construct the next subtrees by simple concatenation, as you see, and concatenating the inverted part of the tree. So that's the idea. Now, how can you make sure that you do not pick two non-orthogonal codes? You see, we have a fixed pattern of chips to spread the data. They're repeated all over again. So it's very simple. Assume you have two low rate data streams, a medium and a high rate data stream. Then we pick, for example, for the low rate, we pick here this spreading pattern, and for the other low rate, we pick this spreading pattern. As long as they are not in the same subtree, you're allowed to pick spreading patterns. For higher data rates, we have to pick a lower spreading factor. So here, for example, we can pick this one. So we have two low rate streams and one mid-rate data stream, and then we could pick one really high rate data stream. As soon as you pick a node you're not allowed to pick any patterns from subtrees. That's the idea. So here we cannot do anything more because now all the subtrees are blocked. So this is a way of supporting 4 data streams with different data rates. But as you can see, you cannot implement arbitrary spreading factors. So that means you cannot support arbitrary data rates because of this way of constructing this coding tree. And no matter how you combine these patterns, as long as you make sure that you do not pick a pattern out of a subtree where one of the parent nodes already picked, it's valid and you can check it out. It's always orthogonal. So that's the way of doing it. So checking if it's orthogonal, you can pick this pattern and then just write it. Well, you have to repeat the upper pattern. And then again, this pattern, -1, -1, 1, 1, -1, -1, 1. And then you can calculate the inner product. That was exactly the idea. If you do this, you will see the result is always 0. So they are orthogonal, a perfect way. So that's the idea. That's how you separate data streams internally. So now that was the CDMA part, CDMA to separate data streams in devices and the devices. Now a bit about the frame structures. In UMTS, we do not need time slots any longer to separate users. We just learned that we separate users by scrambling codes and we separate data streams by different spreading codes. So we do not need the time slots anymore. Still, we have radio frames and we have time slots. Radio frames of 15 slots, 10 milliseconds. And so it was 16 in the first standards, then became 15. So 15 slots, 10 milliseconds. And this slot structure is used for synchronization because we have to send certain information over and over again. For example, what is very important is, and now we look at the downlink here, we transmit the TPC transmit power control information. The problem, it's a CDMA system. We have to perform tight power control, and that means in UMTS 1500 power control cycles per second. So that's quite often, and that consumes also some energy. Okay, because you have to do this in each slot, this is why we have a radio frame with time slots, not needed for the user data. Furthermore, you can see that we can use we have a fixed number of chips per slot, yes, because we have this fixed chipping rate, but as we can use different spreading factors, we can transmit different number of bits. Uplink and downlinks differ how they handle user data and information, but that again are some more details we don't have to cover. So the classical wideband CDMA, as this is called, operates here for UMTS FDD in the paired band. This was our paired band with this fixed chipping rate. We can perform something, I will come back to this, that's called a soft handover. Okay, I will come back to the handover scenarios. We use QPSK for modulation in the classical standard, power control, and we have these different spreading factors depending if you are on the uplink or on the downlink. In addition to the transmit power control information, we transmit so-called pilots. Pilots are well-known fixed bit patterns, resulting in fixed chipping patterns. And with the help of the pilot, you can estimate the interference and the downlink, because you receive the pilot. You can synchronize using pilots, but you also know the strength of the pilot, the signal strength. It's a certain amount of power, the sender, and then you have the attenuation during signal transmission. And as a receiver, you can check the strength of the signal, and this helps you to estimate the interference between sender and receiver. So this can be used as a first guess, also especially in TDD systems, but also in FDD systems for an initial guess for the attenuation, also in the other direction. Additionally, the other side will always send you the TPC commands that will tell you if you have to send stronger or weaker. So this is for power control. So you check the signal strength and tell the other side, please send a bit stronger or not that strong. And this is done quite often, as you can see, 1500 times per second. Furthermore, you see many acronyms like DPD, CH, dedicated physical data channels, etc. This once more is very typical for all these mobile communication standards. Many channels defined, quite complex standards. So if you're interested in this, you have the links at 3GPP where you can look up all the meaning of all these detailed channels. Here, this frame structure is just for an overview that you understand. We are not any longer in the TDMA, but still we have some slotting structure for synchronization, not for user separation. So users can simply send the data. What can we achieve? Typical data rates. So now you see we cannot use an arbitrary number of bit per second in our data channels. If we set up a data channel, there's always an associated control channel to control the data channel. And as you just saw on the last slide, for transmit power control, etc. But you see here, we have a certain number of kilobit per second UMTS can support. And if you want to transmit another number, like something in between, you have to pick, for example, the higher value. So just as an example, if you have a user data rate of 64 kilobit per second, you would pick, for example, 240 kilobit per second. That is supported, a certain spreading, and then you can transmit it plus redundancy, etc. For 144, you use the 480, etc. For typical voice connection at 12.2 kilobit per second, you pick a 60 kilobit per second channel. Well, you see the big difference between the user data rate and the data rate you have on the channel. You need a lot of redundancy. But what you can also see is that you can much better protect the lower data rates here with the spreading factor of 64 compared to the higher data rates, spreading factor of 4 only. That's not that much. You can also see that the data rates for this initial UMTS were not that high, 300 something kilobit per second. That was not really, as the marketing wanted you to believe, the megabits per second. So that was in the very beginning with the UMTS. We introduced the CDMA technology, the spreading, and FDD as one of the technologies. And just to make the picture a bit more complete, there was also a TDD proposal. Never really made it on the market, on the mass market with all the devices. So the mobile phones, they use the FDD, which is more adapted to voice communication paired bands. But there was also the TDD. You remember TDD, you switch the direction of uplink and downlink, and so this can be symmetric or asymmetric, so you can much better adapt to the asymmetric behavior, for example, internet browsing. There's also different spreading factors, but a tight synchronization is needed because of this switching of uplink and downlink. So, as you can see, there are also different TDD frame structures. And this is just one special so-called burst type. There are also others defined. Okay, I just wanted to show you where we use the CDMA. Now, again, I will show you architectures and where the differences are to GSM. We learned that, okay, the multiplexing is different. GSM uses TDMA, FDMA, and here we do not use the TDMA and FDMA for the separation of uses. Furthermore, we do not use different frequencies for different cells. We use the same frequencies, the same channels in all our cells if we want. So this is the architecture of the radio access network. Here you see cells, but in contrast to GSM, we do not have to perform the frequency planning because we could use the same frequency for all the cells because we separate the uses by different codes, different scrambling codes. So that was the difference in UMTS. So how does it look like, the architecture? Well, that's pretty much similar to GSM. The names are different. So instead of a mobile station, we have user equipment. User equipment in the cells. We have node Bs. That's our base transceiver station. It's called node B. We have the radio network controller. That's our base station controller in GSM. And we have our core network. So that's similar to GSM, where we also have a core network. So radio network controllers, node Bs, user equipment, they're all in the radio network subsystem. So the UTRAN comprises several of these radio network subsystems. The node Bs can support FDD, TDD, or both, depending on the operator, depending on the technology. The RNC here is responsible for the handover decisions and does all this signaling to the UE, user equipment, and the cells then offer, finally, the FDD or TDD. So, node B might sound strange. Why not also having a nice acronym? Well, in the end, that was left over. To be honest, someone forgot it, so to give it an appropriate name. What else do you maybe notice already if you compare this in your mind with the architecture of GSM? There's one additional connection, and this is an important connection. We need this. This is here the IUR, the connection between different radio network controllers. This connection did not exist in GSM networks. Why do we maybe need this? Well, now we already touch a bit the handover. I will come back to the handover in some more detail. But in contrast to GSM, in UMTS, a user equipment can have connections to several base stations at the same time. In GSM, a mobile station could have a connection only to exactly one other base station. It could receive signals from others just for signal strength measurement to support the handover. But here we can, for example, forward data from the core network here via node B to different antennas. So we can split up this data stream and transmit this over different antennas. We could furthermore not only transmit it like this, but now assume UE2 having a connection to these two antennas, then we can, also the other way around, receive data via different node Bs, combine it and forward the data into the network. So it works in both directions. So we can combine the data streams, and we can also split it up and send it over different antennas. So now, why do we need this special connection between the RNCs? Well, third scenario, we send data to UE3 or receive data from UE3, and this user equipment is connected to two antennas that belong to different radio controllers. And then we have to recombine the data stream here, and this is exactly when we need this connection. We recombine and send it over into the core network. That means the core network will not notice anything from this situation that you split up and recombine data streams. So, by having these multiple connections to different antennas, the user equipment can perform a soft handover. Because there's no hard switching between antennas, you will rather migrate from one antenna into the other, into the next one. One signal gets weaker, the other gets stronger, and you're just moving between the antennas. There's no hard handover. As soon as you have to hand over the connection, for example, at the core, if you say, okay, the connection, we send over data here, and now we cut this, we send it over here, then again we perform a hard handover. But for the other scenarios, as long as we stay somewhere inside this radio network systems, inside the UTRAN, the core network will not notice anything. We'll only see this single connection. That's the idea. You will see a single connection, and then we further, however, subdivide our data. The core network will not notice. So this allows us to perform a soft handover, and we don't have the need for hard handovers with these problems of prior resource reservation, etc. I will come back to this handover, but for now, this UMTS terrestrial radio access network has to do many things. So here is a list, not really complete, but a list of functions like this network has to control admission, congestion in this network, broadcasting of system information, so cell IDs, etc. Perform all the encryption in the radio channels, the soft handovers, that's important. When I come back to handover, I will explain how we migrate the responsibility inside the network. We have to configure networks. We have to control many of the resources, power control, coding, etc., etc. So this network performs basically everything that is important for mobility support. This just gives you some impression of what we do there. So now you saw the architecture and some of the functions. And now what has this to do with GSM? Well, first of all, let's have a look at the components inside the network. So somewhere here is our user equipment. We have the RNS, but inside you see well-known components like an MSC, like an GMSC, HLRs, VLRs, SGSN, GGSN. Hey, these are exactly the components we used in GSM and GPRS. So the core network is nothing but the core network of GSM plus GPRS. And this saves a lot of money. In the upper half, we have the circuit switched part. So that's circuit switched. In the lower half, we see the packet switched, IP-based part. This goes then to the internet, and this goes then to the classical telephone network. So this is nothing but the classical GSM plus GPRS network. And now you understand why most of the operators already using GSM, they went to UMTS. And if you had ISDN, you pick GSM. And if you had GSM, you pick GPRS. And if you have GPRS plus GSM, then you pick UMTS. So that was a clever evolutionary path. What else do we see? We see that we have many other layers. Yes, that's quite typical in communication systems. We use IP, well, like in the internet, as we know it from GPRS. But now we use as underlying technology ATM. ATM was a big hype, I'd say, in the early 90s, mid-90s. And this was roughly the time when 3GPP also standardized UMTS. Maybe today they would pick something else, as we'll see with LTE. But here we picked ATM. So you see the ATM asynchronous transfer mode as a layer 2 technology here. I will come back to this. So, but for now you see, okay, the core network is basically the same we had for GSM, only the radio access, that's different. And we have different technologies for voice. So the classical voice call takes this path, and data transmission, well, you take another path. So you have these two paths inside the system, a circuit switched and a packet switched. And we will learn that LTE will drop the circuit switched part and only the packet switched part remains. But for now, we have those two parts. So the legacy from GSM, which helps to save a lot of money. Furthermore, here you see the integration of a classical GSM radio access part, the BSS, and the UMTS radio access part, the radio network subsystem, with the BTS and the Node Bs, the BSCs and the RNCs. But the core network is identical. So there's no difference. You can use the same components. But that also means for a mobile station / user equipment, you can roam, hand over from a BTS to Node B and vice versa, if this is supported by the operator. So that depends on the operator. But look at the standards, it's feasible. Especially important was the handover from a UMTS Node B to a GSM network, because in the beginning you didn't have the full coverage with the 3G technology. This is why all the mobile phones and the operators offered this handing over the call without interruption from UMTS to GSM. Typically not the other way around. Well, the standard allows this, but not implemented. So where do you invest a lot of money? Well, yes, it's the infrastructure. So the core is expensive, but also setting up all the antennas, etc. is expensive. So this is why, as a network operator, you're quite happy that at least the core is more or less the same. Remember, a circuit switched part with the GSM components, so that's circuit switched, and a packet switched part with GPRS components. So the release 99, and that was the idea during the introduction of UMTS, release 99 uses GSM GPRS network and adds new radio access. Saves a lot of money, much faster deployment, but this is not as flexible as all the newer releases. If you look into the newer releases, you will find many more technologies that cannot reuse the old systems anymore. I will come back to this when we look at LTE, which is now the dominating technology. So those two domains, a packet switch, the circuit switch, is also reflected in the protocols. So the circuit switched domain uses classical protocols like, for example, ATM adaptation layer 2. So this classical telco technology for transmitting so-called cells of 53 bytes. And the packet switched system also uses ATM adaptation layer 5 here. But as we learned already from GPRS, some more internet protocols to offer this IP tunnel where we can then transmit our IP packets into the internet. And here we connect to a classical ISDN network, GSM, whatever. So you see, looking at the protocols, okay, we introduced in the radio access network some more ATM components, but the remaining protocols, okay, well known. Packet switching, circuit switching. So this was not really a revolution when you look at the core. The revolution was using CDMA instead of TDMA, FDMA. Some questions. Now, if you look at different data rates, high, low data rates, how do they influence the robustness of the transmission UMTS? Think of narrowband interference. Think of what kind of applications actually fit to these effects. What kind of applications would not fit? Maybe you need something UMTS cannot offer. Think of different usage scenarios of high and low data rate. You know we have the near-far effect. So what does UTRA-FDD do? We have the problem of near-far. What can you do against it? You learned a bit about this spreading, the different factors. What is a drawback? How do you compensate this? There are some tricks. Maybe you find something interesting in literature. How, once more, do we separate different data streams of different users? How is this done? Where do you apply which type of code multiplexing? Once more, compare the architecture of the UTRAN with the GSM. What are the major differences in the radio subsystem? Why do we have this difference? There was one major difference. What is it used for? You should know this.